Hi, my name is Keus, and I'm going to tell you about CP-Violating Inflation, which is a work I've been doing with my collaborator Kimmo Tuominen in University of Helsinki. Let me start with a bit of introduction with the standard model of particle physics, which is the best theory we have so far describing nature. Its current formulation was finalized in the late 70s, and time again it has been confirmed by experiment with the observation of many of the particles that they had predicted. With this last missing particle, the Higgs boson, well, let's say a Higgs boson, which was discovered in 2012, which was predicted by the Brout-Unglet-Higgs mechanism 50 years prior. So as successful as the standard model of particle physics is, and as in agreement as it is with experiment, there are many phenomena of nature that it fails to address, such as a dark matter candidate. None of the particles in the standard model are suitable dark matter candidates with the properties that we expect from a dark matter candidate. Observations show matter-antimatter asymmetry, which the standard model fails to provide an explanation for. One of the best motivated baryogenesis mechanisms is electroweak baryogenesis. And even though the standard model contains the ingredients for electroweak baryogenesis, it still fails to give an explanation or produce the correct amount of baryon over antibaryon excess. The reason is that the electroweak phase transition in the standard model is now the first order phase transition, and the fact that the amount of CP violation in the standard model is about 11 orders of magnitude below what is required for baryon asymmetry. Also, the standard model fails to provide a natural inflation framework. The fermion masses in the standard model are basically free parameters that are measured, and they differ by a few orders of magnitude, and the standard model gives no explanation why that is. Also, the electroweak vacuum in the standard model doesn't seem to be stable, and the standard model doesn't give any explanation why the vacuum hasn't decayed to a deeper minimum. For these reasons, we know that to find the ultimate theory of nature, one needs to go beyond the standard model. And one of the best motivated beyond standard model frameworks is the scalar extensions of the standard model. The scalar sector in the standard model, which is comprised of one Higgs doublet, is the experimentally least constrained sector and least understood sector. And extending this sector allows for many well-motivated theories which will address many of the standard model deficiencies and are accessible by many current and upcoming experiments. Let me briefly justify why I think 3 Higgs doublet models are the best scalar extensions. The reason is that in more economic scalar extensions, such as the singlet extension of the standard model or the doublet extension of the standard model, trying to at least, let's say, address the 3 most striking shortcomings of the standard model, the dark matter CP violation and the inflationary framework, they are not compatible with each other, and some don't even allow for example, introducing CP violation, such as the scalar singlet extension. In the 3 Higgs doublet models, however, one can not only have very exotic and new dark matter and CP violating phenomena, but also very interesting inflationary phenomenology, which I will talk about here. And just as a bonus point, 3 Higgs doublet models, which were originally suggested by Weinberg in the late 60s, also have very interesting implications for the fermion mass hierarchy and, well, stability of the electroweak vacuum, which I won't have time to talk about, but please do ask me later if you're interested. As I mentioned, the scalar extensions are accessible by many current and upcoming experiments, which, again, I leave the slide for you to look at later because I don't have time to go through it. But basically, talking about inflation, which is one of the best in agreement with observation frameworks that we have for describing many observational facts about the universe, such as the homogeneity and the flatness of the universe. And one of the best in agreement with observation in inflationary mechanisms is the slow roll inflation, which basically predicts scalar field called the inflaton, which is represented here by this field phi, which basically has a very flat potential at high field values, and it slowly rolls down its flat potential, and at the end of inflation rolls down to the minimum of the potential, where it basically oscillates and dumps its energy into the standard model particle content in a period that is known as the reheating phase. So as you may know, the Higgs inflation basically says that we have the one scalar that we have in the standard model, the Higgs boson. Why don't we assume for the scalar for this Higgs field to be the inflaton? The problem is that we know the scalar potential in the standard model, which is of this form, and for the potential to be flat enough to be eligible as a slow roll inflation, this quartic coupling has to be around 10 to minus 16. But we know in the standard model from basically the Higgs mass measurements that this coupling is around 0.12, which is much, much larger, meaning that the potential is not flat enough. A way of flattening this potential is for allowing the Higgs boson to couple to gravity through this coupling C, which is known as the non-minimal coupling. But again, for the Higgs potential in the standard model to be a kind of flat enough potential for the slow roll inflation to work, this C parameter has to be quite large. And it is in this sense that I mean that the standard model cannot accommodate a natural inflationary framework. So the solution would be to, let's extend the scalar potential. And as I briefly try to motivate different extensions of the standard model, I'm hoping to be able to, convince you that a 3 Higgs doublet model is the best motivated and the minimal scenario for addressing not just the inflationary deficiencies of the standard model, but many other shortcomings. So what I'm trying to do here is that I extend the scalar sector by adding 2 extra doublets with basically the same quantum numbers as the Higgs doublet. But also I impose this extra symmetry, a Z2 symmetry, on the full Lagrangian, under which these 2 new doublets are odd, which is why I've denoted them by the color red, whereas phi 3 is going to play the role of the standard model Higgs doublet, and it's even on the Z2 symmetry. It is in the context of this Z2 symmetry Higgs doublet model that for the first time we introduced CP-violating dark matter with very interesting phenomenology. So let me tell you what are the extra benefits of this Z2 symmetry. So here it is, its generator, which basically tells you how the Higgs doublets transform under this symmetry. Here are phi 1 and phi 2, which basically transform non-trivially under this Z2 symmetry, meaning that they're odd under this Z2 symmetry, while phi 3 transforms trivially, meaning that it's got an even Z2 charge along with all the other standard model fields. Also, the vacuum respects this Z2 symmetry, meaning that the 2 dark doublets or the Z2 odd doublets don't acquire a vacuum expectation value. So they're also referred to as the inert doublets, while the phi 3, the Higgs doublet, is the only one that does acquire an vacuum expectation value. So here I've simplified the particle contents of these doublets, ignoring their charge components for now. As I mentioned, we impose the Z2 symmetry on the full Lagrangian. So not only the scalar potential, but the rest of the Lagrangian is also Z2 symmetric, which means that only phi 3 is allowed to couple to the fermionic fields. So what this does is that it forbids flavor-changing neutral currents, which have not been observed in experiments. So if your model allows for them, you have to justify why they haven't been seen. And by imposing this Z2 symmetry, you basically forbid them. And as I mentioned before, CP violation is going to be introduced in this dark or inert sector. And as you may know, electric dipole moments are the one of the probes, or one of the most constraining probes of CP violation in beyond standard model theories, which basically are mediated through processes of this type at one loop and through bar Z diagrams in a two loop. But as I mentioned before, the only scalars that are allowed to couple to fermions are the scalars from the phi3 doublet, which is basically the standard model Higgs doublet, which doesn't have any CP violation. The CP violation is introduced between the dark doublets, which aren't allowed to couple to fermions anyway, which means that I can introduce a large amount of CP violation without running into the constraints from the precise measurements of electric dipole moments. And it is, as I mentioned, in this context that we studied CP violating dark matter with very interesting and novel phenomenology. So looking back at the scalar potential, we know that we can write this Z2 symmetric potential as two separate parts. The part that is phase invariant, which by construction doesn't allow for any complex parameters. So this part of the potential is CP conserving. And a Z2 symmetric part of the potential, which is when added to the phase invariant part, makes sure that the potential is only Z2 symmetric. This part of the potential does allow for complex parameters, meaning that you can introduce CP violation into the scalar potential. But also when you write your full action of the model, you see that the non-minimal coupling to the gravity also is allowed to be complex. This is the novel kind of signature of this model, which yeah, I'm quite proud of. So to show you the effects of the CP violation, both in the Higgs potential and in the coupling to gravity, non-minimal coupling to gravity, I only keep lambda 1, which I write as the modular of the field and a phase phi 1, and Xc4, which again I write as the moduli of Xc4 and a CP violating angle theta 4. So what you will see in the next slides, I have tried to parameterize it in terms of theta 1 and theta 4. This is not to say that these other parameters cannot be CP violating. It is just that I'm trying to simplify it for you to show exactly what the effect of the CP violation is. So as you can see, this is a multi-field inflation scenario, which is solvable numerically, but here I'm trying to solve it analytically. So I use a couple of simplification relations where I write the fields, the other fields from the inert doublets, which contribute to inflation, as proportional to H1. To remind you quickly, these fields are the neutral fields from the two inert doublets. I can set it to 2 to 0 because it is I have a rephasing freedom. But the other two fields, eta 1 and H2, I set as proportional to H1. These beta 1 and beta 2 factors can be time or space dependent, so I'm not trying to constrain the model. And you need to make sure that you find the direction of steepest descent, which would be your direction of inflation. And once to analyze the model, you go from the Jordan frame to the Einstein frame, and you use these reparameterization coefficients. You can basically write your inflation field or inflaton field as in terms of this reparameterized inflaton field A tilde. And you see that I show the plots in terms of A tilde. So once you write the inflationary potential, you see that it has the Sorobinsky form with a bunch of parameters that are sucked into this X function, which has the CP violating parameters from the potential and from the coupling to gravity. So just showing you what the inflationary potential looks like, or basically that it is in fact slow roll. You see that the high field values, so in terms of A tilde, if I'd written it in terms of H, you would see that it'd be like very high field values. the potential is basically flat, and towards the end of the inflation, it rolls down the inflationary potential into the minimum. And these are basically the potential for different values of θ1 and θ4. So what you need to do when you've put an inflationary model together is that you have to show that your model basically agrees with observation. And some of the observational quantities we have are basically the spectral index and the tensor to scalar ratio. And here I'm basically showing you for appropriate number of e-folds, the model basically sits in a region very well in agreement with these observations, which are basically polarizations of the cosmic microwave background spectrum. Since I'm short in time, I'm just going to go quickly through these slides, but please do ask me later if you want more information. So another one of these observational parameters that one needs to abide by is the scalar power spectrum, or PS for short, which has been measured by some accuracy. And usually what you do is that you need to show that for different values of your non-minimal coupling to gravity, you basically fall into the region that is in agreement with experiment, whether at 1 sigma, 2 sigma, or 3 sigma difference. So what I'm doing here is that for a typical value of, or a given value of θ1, I'm showing you that for different values of θ4, you can have different values of this non-minimal coupling to gravity to satisfy the observational constraints. And here, what I'm showing you is that because you have these extra parameters to play with, you don't have to try to basically, you can basically predict the central value of PS. So I've fixed my PS prediction for the model to be at the central value that has been observed, and I'm showing you that for different values of θ1 and θ4, you can basically, with different values of this non-minimal coupling to gravity, you can abide by the observational bounds. So what basically this model has now, which is its winning point against the Higgs inflation, is that in the Higgs inflation, you have this non-minimal coupling to gravity and the one basically coupling from the scalar potential, which forces you to have a very large C to agree with observation. Whereas in this case, first of all, I have an extended scalar potential. Also, I have these CP violating angles. So here I've chosen lambda I of 10 to minus 3, which is why my C4 values are quite large. Note that all experimental and theoretical constraints allow for my lambda I to be very small, of the order of whatever, 10 to minus 20, 10 to minus 10. And by changing this, these lambda I can basically, my C4 could be as low as 1/6, which is the conformal value for C, but still basically predict exactly the central value for PS, which is the winning point of this scenario. I don't have that much time to tell you what are the basically phenomenological consequences of these CP violating sources, not just through the inflationary potential, but also through non-minimal couplings to gravity. But basically the idea is that you can transfer this CP violation to the fermionic sector and basically use it for baryogenesis. Since I'm running out of time, I'm going to leave you with my summary slide where I basically tell you that there are many scalar extensions. The very economical ones run into many problems, whereas the 3 Higgs doublet model is the one that basically could give you very interesting phenomenology, especially in dark matter and CP violation and in inflationary directions. Thank you very much.